Hello, this presentation is titled Chess Positions and Knight's Tours via Graphs in Raku. My name is Anton Antonov. Today is December 8, 2024. So December 8 is actually a holiday in Bulgaria for the Bulgarian students. It's a holiday which started 120 years ago, 121 maybe. So in this presentation we're looking into two ways of plotting chessboards. We're looking into Knight's Tour graphs, Hamiltonian paths for those graphs, and animations of Knight's Tours. I'm going to be using the Raku package graph and its functionalities, its algorithms, methods, so forth. And I'm going to use the framework GraphViz for visualizing graphs in order to visualize chessboards. So I have a dedicated Raku package called graphviz.chessboard for visualizing chessboards using the dot language and how it's being converted into whatever formats. Dot is the specification language of GraphViz for graphs, for specifying graphs. An alternative way of plotting chessboards is going to be shown with JavaScript D3, and this is a little bit too much talking without much imaging. Let's actually show a chessboard here. I have selected some colors and so forth. I have specified that I want to have 4 rows and 6 columns here, and I have specified the size of the chessboard. And we're converting this into SVG. If I don't convert it into SVG, this is going to be the dot language, actually dot language in HTML. So let's actually do it like this. Now you can see here that this is the dot language specification. We can almost see all of them, right? And so yeah, basically this graph specification has been generated by this function dot chessboard, and then if we render this image to SVG, we can display it in Visual Studio Code, and SVG is being rendered directly. All right, so I can do some other chessboards using annotation here. This is a list, two lists, a list of two lists, or a list of two triplets. A1N, capital N means white knight, and B3 Q. So lowercase q means black queen. So this is what we see here. We can visualize this with JavaScript D3. JavaScript D3, this function is actually using heat map plots, right? So I'm not going to dwell too much on this, but yeah, we can also use the same notation as above here, and we can also use Fen strings. Fen is Forsyth-Edwards notation, and so it's nice to have this kind of visualization. And so you can see this particular visualization where it says Fen string, where it says is what we have 3 empty rows, like this 8 means that we have empty squares. Then we have on the 4th one we have 3 empty squares, white king, and 4 empty squares, and so forth for the rest of the specifications. Same thing is with JavaScript D3, right? So it is an interesting question. Can we visualize we can visualize obviously smaller chessboards or larger chessboards with dot chessboard, but can we process the Fen strings? And I think the recent additions, updates of Fen grammar, which is being used here, they allow for more generic chessboards, chessboards different by 8x8. All right, so where are the graphs here? And this was probably too much of a warm-up. So you can see this is a chessboard in which I have specified, for which I have specified this grid graph 4x6. And let me actually change the, you can see that this is a grid graph, and the grid graphs are bipartite. That's a property. So yeah, so you can see this is a grid graph, and I have visualized, I have colored the nodes in a particular way, like say white and black, or gray and whiter, kind of whiter than gray. So you can see here dim gray, light gray have been used. As I said, grid graphs were bipartite. So bipartite means that you can separate the vertices of the graphs into sets, and the nodes in each of the sets connect only to nodes of the other set, not between each other. And so this is exactly the case here. So there's something else I would like to mention happening here. So actually, let me return to the previous state of this diagram. So I'm going to return this. So I have this grid graph. If I just make the vertices bigger, I'll basically get a chessboard. So if I don't produce an SVG, right? And if I show you what this is basically the dot specification. This is the dot code. This is the dot spec, or the dot language of GraphViz. So GraphViz knows how to convert this dot code into whatever kind of diagrams, be that SVG, PDF, PNG, and so forth. So this here, what you see, I'm actually interested in this dot spec, and I'm removing the first and the last lines, meaning I'm removing graph, and I'm removing the curly brackets at the curly bracket at the bottom. And so now I have this graph specification, which I can combine with other dot specifications to produce more complicated plots. This is kind of the big secret here, I would say. So let me see. This should produce an image. Yeah. Okay. So let's actually look into a Knight's Tour graph of a chessboard. So the package graph knows how to produce this kind of graphs. So you can see it here. So this is 4x6 chessboard, and I have put a prefix KT to each of the vertices, and we have this this graph. So you can see that from each node, if a node is connected to another, this means that we can make this knight move to that node, right? Okay, there's an interesting question. Can we make a Hamiltonian path through starting, say, with this node and finishing to this node? Or actually starting from this node and finishing anyway. Hamiltonian paths, this means that we are going through all of the vertices only once. So two conditions, all of them, and second condition, the first condition is all of them, second condition is only once through one of these nodes. So let's actually see how is this being done. This, unfortunately, usually this method is not as slow, but actually let me see, maybe if I use whatever. So this here was basically saying, I'm saying, okay, well, we can finish to whatever path. And so I'm going to try to opportunistically change this a little bit in order to see can I get faster result. Yeah, so with certain configuration of graphs, I get somewhat slower performance of this find Hamiltonian path, but you can see now it's actually pretty fast. I'm using the so-called Warnsdorf rule, and I explain what it is. If I don't use it, this is generally slower, but if this rule is being used, it's much faster. Warnsdorf rule was created for Knight Tour graphs, for the solving of the problem having a Hamiltonian path with the knight, but apparently it applies to wider range of graphs met commonly in practice. So if we keep track of the nodes we have visited, basically the degree or the number of possible places we can go, possible vertices we can go from a given vertex, if this is our path, say, finishes here, this changes, right? So we are choosing to go to such a vertex in which the extensions are the smallest, the possibilities are the smallest. So this is what Warnsdorf rule is. I think it was described more than 120 years ago, I'm not sure, more like 140, 160. Anyway, it is applicable in general. There's another algorithm which I implemented. It's called Anglo-invariant algorithm. And you can see, for example, if I didn't use the Warnsdorf rule, the random path finding would have been faster. And so there's some motivation for this, right? It's not actually as good or as reliable, but very often you can find much quicker for certain Hamiltonian paths, and that might be a desirable feature. All right, so both of these algorithms, backtracking and random, were implemented obviously in graph, and so let's actually visualize one of these paths. So here we can see this is the path we got. and we finished in this in here at the bottom. Let me actually return to this KT03. This means this top left node, right? Instead of in whatever. This is actually a nice feature, I would say, for the Hamiltonian path to be able to specify the whatever finishing, right? And so this here with the whatever finishing, we can see that our end node is here. And I'm doing something else here actually. Let me actually show you. So here I am, if I don't do the vertex renaming or replacing, if I just keep the original vertex names, yeah, these are the original vertex names of the night tour graph. But this probably it's not very convenient if you want to know where you are at, right? Like, so which one is this? Is it the fifth one? Is it the sixth one? And etc. So I might want to have both notations in one way or the other, but one way to deal with this is to have this vertex rename. And so you can see this actually was the 20th in order, right? Place we have jumped at. So let me actually return this to be a circle. You can see here for renaming. Renaming takes this list of pairs, right? How the vertices are renamed, and you can tell me, well, why didn't you use KV, whatever, right? Yeah, you can. Yeah, we just for some reason, actually I'm not sure, but for some reason I actually thought this notation is somewhat more expressive or more obvious what exactly is happening. All right, moving on. So making animations, that's actually an interesting problem. And so let's actually, first of all, why I'm doing this? Well, it's an instructive exercise to figure out with, can we make animations in Raku in general with anything? And I think, this is what we're going to see. We can make Raku animations using SVGs. I also put LLMs here when initially made this presentation. I'm actually not that interested to show the LLM functions, but I did ask LLMs to, with this kind of prompt, to generate animation code, right? I'm not going to demonstrate it here. So I have this points, for the jumping, and let me actually do the actual transformation. I'm actually extracting the transformation, which is being used when the images are being scaled. And now we have this image, which it shows us animation of this point disk, how it moves from the beginning of the path to whatever the end is. All right, well, kind of sort of good. Can we do better? Like, for example, can I actually do something like, say, like actually display the for example, the knights jumping, and also showing one jump at a time. So you can see what I'm doing here, right? If I select one, if I select only one element of the path, right, the first element only, we get this. If I select, say, 4, 5, we can get all of this 4, 5 jumps, and etc. So maybe I can use this progressive path to kind of make these images. I can make images for all of them, for all of the all of this knight moves or knight jumps, and then make an animation from it. There are several ways to do that. I see 2. We can make a background chessboard and then have the consecutive images, the dynamic images, like the knights, the figures of the knights or the pieces, to be moving around, right, to be animated. Alternatively, we can make the full chessboard, right, for each of them. So you can do that, and then basically animate the list of images. This is actually a more universal solution, and if we know how to implement it, it's probably worth to make it as a universal solution for Raku to make animations of SVG images. So here, what I did is that I made the partial tour knight jumps. So I didn't actually plot the knights. I didn't find it informative, to be honest. This is more informative. So basically saying you take the first 4 moves and you make this partial path. So you can see here I have made the SVG graphs, right? Graphs, plots. I have made the plots, and yeah, they're all based on graphs. And you can see I'm using subgraph. So basically, from the path itself, we're taking a certain subgraph up to certain value and so forth, right? And basically making these progressive jumps. And so here I'm making some additional manipulations of the actual graph names, because they all have graph 0 as an ID, and I'm changing the ID to say 0, 1, 2, and so forth, right? This is what is happening here. And we are actually, I think, ready to make the animation plot. So yeah, this is what the animation plot is. Again, this actually is a fairly nice functionality to have in general, as a general solution, not just say for knights and chessboards and whatnot. So I'm going to play this one more time, and yeah, well, and I guess this is the presentation. Thank you for your attention.